Okay, morning everybody. So we're going to start doing physics today, and I've mentioned to you before that physics is my personal favorite, so I hope you guys will enjoy it as well. A couple of thoughts. Physics is not just math. Okay. Sometimes you might hear about a reputation about what physics is like. You will need to do some math in this section here. You'll need a calculator, but I am more than fine if you just use the calculator on your phone. That'll work. You may prefer to have a slightly more advanced calculator just for your own ease of use, but like we will do some basic calculations in physics. That being said, I don't believe my personal philosophy about physics is not that it's about doing math equations. Otherwise, we're just doing another math class. Physics is really about understanding how the world works. Physics is about concepts. And that's one of the reasons why I love physics, is not because of the math part, but because it really tries to explain what makes the universe tick. How do things work the way they do? And that's where I'm going to start here on this first slide. Physics is all about the study of natural phenomena. And that's maybe a bit heavy, so let's break it down a little bit simpler. It's really about energy, matter, and how they're related. Okay. We talked about matter in chemistry. What is matter? Matter is all of the stuff in the universe, right? If it has protons, neutrons, electrons, it's matter. But if we had a universe that was static, if you don't know what the word static means, like stationary, not moving, like not changing, I just point to the stuff on my desk right here. Here's a water bottle, here's a binder, they're just sitting there. That's a very boring universe. We do not have a boring universe. We have an exciting, active, dynamic universe where things are constantly changing. We're eventually going to get to biology, and we're going to talk about life and how when you put energy and matter together, you can create cells that are living. I mean, those are active processes, right? Our question then is, well, how are they related? The name for physics is actually from the ancient Greek for nature. It's from the ancient word physica, and it's all about nature, like trying to understand really these words here. How does our universe behave? Right? I think this stuff is cool. And I honestly think that everyone should take physics courses. You know how, you have to take English and social to graduate? Honestly, I think it would be nice if physics was a requirement for graduation, but not like physics in the way that like you have to do a whole bunch of crazy math equations, but like people should learn about how energy works in our universe, and people should learn about quantum physics because it's kind of cool. It would be nice if you didn't have to get tested on things, which is why we're not doing that, right? But it'd be kind of cool if you could just learn physics just for the fun of it, because I bet you if you took away the math and if you stripped away the grades, I think almost everybody would love to learn about physics because it's kind of cool if you like to learn about things. There's actually two main branches of physics. The first is called classical physics, and it involves laws of motion of everyday life stuff. So we're talking about normal size objects like you and me and a baseball and a car and trains and airplanes and the physics behind how all of those objects move. And for hundreds of years, that's really what physics was about, was what we call classical physics. Sometimes we call it Newtonian physics, in honor of Sir Isaac Newton, who was honestly one of the people who figured out most of the principles and equations behind it. But what I love is modern physics. And I've already tried to share with you little bits and pieces of modern physics. There are some really cool things in what we call the quantum mechanics and general relativity. You probably recognize Albert Einstein's name. He was really instrumental. Maybe you've heard of the thought experiment called Schrodinger's cat. Ever heard of that one before? Yeah, I actually even have one of my students last year gave me 2 mugs to help represent Schrodinger's cat. I don't have time to go through all of that because, I mean, that's an entire Physics 30 course. But there are some really cool ideas about how teleportation might be possible, time travel, multiple universes. If you watch, like, I don't know, Marvel movies and comic books and they talk about the multiverse, there are some legit theories about how we may be part of a multiverse and how there is a you in another universe who didn't come to class this morning, and there's a you in another universe who actually lives in France instead. Like there are some really cool theories in physics. And what I love about all that stuff, by the way, is that, again, they're not really about the math, but just about like the cool thinking about what is our universe at its core. Like, how did it start? How will it end? There's theories about, say, the Big Bang Theory. Probably heard that one before. There are theories about how our universe will one day end. 2 of them that are known. One's called the Big Chill. One's known as the Big Crunch. Anyways, I don't have time to go into all of these things, but like once I get going, I get going. Okay. That's what physics is about. We're going to focus on energy. Since it's kind of your first unit on physics, our main goal is to talk about what is the energy, or energos, the Greek word, meaning active, that keeps things moving. And today my lesson basically is going to describe historically what did scientists think they knew about energy. Okay? We're going to finish off talking about what we currently believe about energy, but we're actually going to walk through kind of a timeline like we did in chemistry. If you guys recall a day in chemistry where we talked about a whole bunch of different scientists and what they thought and why they thought it, we kind of do that in physics as well, and we'll do this in biology. There's sometimes a little bit of like a social studies history overlap, where before we figure out where we're going to go with this, it really helps to know what the past people knew, why they thought they were right, why they might have been wrong, and how we grew from it. So that's more or less the concept of my lesson. Before I get there, though, I am going to start at the end. We're going to talk about all the different forms of energy, because we live in the 21st century. You're probably familiar with all of these forms. But if you can, in a few minutes, I want you to put yourself into a mindset of someone 300-400 years ago. They wouldn't have known about nuclear energy, right? Nuclear energy wasn't discovered until about the 1930s, 1940s. Actually, what was the really big event in the 1940s where nuclear energy was used for really the first time? Anybody know what I'm referring to? Yeah, the bombing of Japan at the end of World War II, right? And so nuclear energy is a relatively recent energy that we've only just discovered. I'm going to talk to you in a few minutes about magnetic energy, but why don't we start at the top here? Thermal energy. That's the one we just finished talking about, right? What is the alternate word we usually use for thermal energy? That'll work. I was actually just looking for a small 4-letter word. Heat, yeah. When we normally talk about for thermal energy, we talk about heat. Infrared works, though, too. Those all often go side by side. I will likely ask you this at some point on some sort of, assessment. Okay, what is heat? Okay, heat is molecules that are vibrating. But that's really not enough, okay? I mean, all molecules are vibrating. If something has more heat than something else, the more heated object causes its vibrations to go to the quote-unquote colder object. Because there's no such thing as cold, right? We've discussed this. Cold is really just the absence of heat. When you feel cold, you're feeling your molecular vibrations causing the air around you to vibrate more. And through that loss, finger quotes, loss of energy, that's what you're feeling as cold, right? Heat is about vibrations, and certain things feel hotter or colder depending on their ability to transfer that heat. One of your questions on your performance task is about the pie that comes out of the oven. Why does the metal feel hotter than the pie itself? They're the same temperature, right? Both the pie and the metal the pie is in is both 400 degrees Fahrenheit. But the metal transfers its heat vibrational energy easier than pie crust does. So, okay, moving on. That's thermal energy. Chemical energy is something that was discovered probably a couple hundred years ago. The idea of being able to use chemicals and create a battery. And if we can create a battery of some type, then we can use chemicals to do something useful. Most likely, chemical energy will actually be in conjunction with electrical energy, most likely. That being said, chemical energy is not just the energy in batteries. Our body basically uses chemicals to give us energy. Only the chemicals that our body intakes are food. Right? But in that same sort of way, right? We intake food as quote-unquote chemicals. Our body then digests that food, uses it from a biological process to give us chemical energy. But like I said, lots of times chemicals often go with electricity as well because you're talking battery power. Radiant energy then is something we also just recently discussed, right? Radiant energy is the energy from the sun in the form of X-rays or infrared, right? Infrared linking back to thermal. Light. Well, no, not sound. I'm getting to that later. X-rays, radio waves, microwaves, right? All of that is radiation. Nuclear energy, like I said, a form of energy that wasn't discovered until basically 70, 80 years ago, somewhere in that time frame. And the Manhattan Project, a whole bunch of scientists came together, and historically the context was Albert Einstein, who was, he used to live in Germany as a Jew, moved to the United States, basically said to the President of the United States, we need to start working on nuclear technology. Because if the American scientists don't figure out how to build a bomb, the Germans will build a bomb, and that would be catastrophic because then Nazi Germany would be so powerful. The U.S., like, you can imagine the scenario if Nazi Germany decided to drop a nuclear bomb on New York City, how would that have changed? How would that have changed history, right? So, anyways, Einstein writes to who was it? I have it on my board there. FDR, Franklin Delano Roosevelt was president at the time, and says, "You guys need to start working on this bomb. Otherwise, the Germans, who knows what will happen, right?" And as history goes, they actually managed to defeat Germany without the use of the nuclear bomb, but they did drop it in Japan, though. Okay, this next form of energy I'd like to actually demonstrate to you. There's a form of energy known as magnetic energy. And this is actually a really cool principle here. What I have right here is just your basic bar magnet. And what I've got here is a basic spool of wire. All that's happened is this spool of wire is running around in circles, and I've got lead clips just attached to both sides. Okay. This is magnetic energy. If I can take a magnet, and watch this. Can everybody see the little dial on here? Okay. It's going to be subtle. This is measuring just a small amount of energy. But watch what happens when I take the magnet. Oh no, I lost my connection somehow. It was working a few minutes earlier. Of course, that just destroys everything. No! Hang on, bear with me. Oh, no, it's so embarrassing. I have like a faulty connection somewhere. Well, wasn't this useless? There we go. Okay, I got it to work. Okay, did you guys see that? I'm going to take the magnet. I'm going to put the magnet inside the coil of wire. Oh, there we go. Can you see how that's causing the wire to move just a little bit? It should be better. My connection is really poor somehow. One of these clips is not staying on properly. All right, one more time. If not, I'm just going to have to describe what happens because I'm wasting our time here today. Clip nicely, clip nicely. How was Halloween for everybody? That's good. Oh, goodness. Okay, I don't know why the connection didn't work, but did you guys happen to see it worked like just briefly for a second there? When I took the magnet and put it inside the coil of wire, did anybody? There we go. There we go. Okay, you got to see this before it stops working. Do you see how me moving this magnet around this coil of wire, just kind of like in and out and back and forth, how it's causing the dial to like move a little bit there? You guys see that? Okay. This was actually a really important discovery. It happened in the year 1831 by a guy named Faraday. And Faraday discovered that if you took magnets and moved them around a coil of wire, you could actually make electricity. And that's magnetic energy converting into electrical energy. We actually use that principle in southern Alberta in a much larger fashion than what I showed you right here. What do we have in southern Alberta that we use to try to make electricity? The windmills, yeah. And now what I was doing is I was manually taking a magnet and making it in the coil of wire basically move in and out and back and forth. But what we have in southern Alberta is these big windmills. They run on a turbine. And a turbine basically spins around in a circle getting pushed by the wind. Well, that's basically this magnet getting pushed in and out and in and out in a circle basically around a coil of wire. And as you're able to see, it can make electrical current. That was actually a really important discovery form of energy, is the magnetic energy, which can then be used to make electricity. Elastic energy you're probably familiar with, right? Just the idea of, pull back on an elastic band and shoot something forward. Sound, hopefully I don't need to articulate too much. You get the idea of sound being a form of energy. Mechanical energy I want to spend a few seconds discussing. Okay. Some people sometimes mistakenly think that mechanical energy is all about machines. That's actually not the definition. It's not about mechanics. It's about anything that is in motion. It's a generic term for things that are moving. And so if there is an object that I've thrown across the room, it would have mechanical energy because it's moving. It's in motion. Okay. Sometimes we like to use the word kinetic energy to describe that as well. Luminous energy, very specifically light, although to be honest, it's very similar to radiant energy. And then the final one, which we're not going to discuss in this course, but there is mass energy. This is a really cool formula. I'm sure you've seen it before. E equals mc squared. We learned about it in Physics 30. M is mass and E is energy, and there's a formula that relates how mass can actually be used to make energy, which is super cool. So, anyways, just a brief slide there discussing some of the forms of energy. Here's what I want to do for the most of our lesson, though. I want to discuss historically what scientists thought about energy, because most of what we currently know about energy is a fairly recent discovery. I want to discuss the history. So let's start way back when, in basically like 500 years BC. We've actually discussed this theory before. This was Aristotle. Pretty good. Okay. Aristotle had a theory about chemistry that kind of bleeds into physics. His chemistry theory was there's only 4 things in the universe. There's some mixture of your earth, air, fire, and water, the 4 basic, what he thought were elements. Aristotle was very wrong. In fact, none of these are elements. Earth is not an element. Air is kind of an element, I guess, if you consider the oxygen and nitrogen to be elements. Water isn't an element. Water is a compound, good. And then fire isn't an element at all. Fire is basically an expression of a few different forms of energy. There's thermal energy in fire. There's radiant energy in fire. There's luminous energy in fire. You could probably argue there's sound energy coming out of fire. Now, long story short, though, Aristotle was very wrong about his theory, but this would have been one of the first discussions of energy. What I'd like to do is I'd like to share with you then one of the applications that a scientist, I'm not even sure a scientist is how he would have defined himself. His name was Hero of Alexandria, and he made what we now recognize as the first turbine. We just a second ago discussed the concept of a turbine and a wind turbine. What makes something a turbine is it just spins around in circles, right? And if you can get something to spin around in circles, you've now created mechanical energy. Remember that, talking about that term there? The energy of motion? A lot of what we're going to discuss today is that physics wants to create mechanical energy. We want to get things to move. I want my car to move. I want bridges to lift up and down. I want cranes to lift beams up in the air, right? Physics is all about moving objects sometimes, right? So a turbine, if you can get something spinning around in circles, that can be useful. Now, to be honest, Hero's engine right here was basically just a little toy. Let's see if we can kind of figure out from the picture how this works. He heats up a fire. Inside this little dish right here is probably water. What happens when you boil water? It turns into steam, right? So there's a whole bunch of steam starting to build up inside here. And as the steam builds up inside, based on the design of this, the steam vents this way and vents this way. What do you think is going to happen to the little ball? It's going to spin. Now, okay, this was probably a novelty. I mean, this would have been like the 2,000-year-old version of a yo-yo, if that makes sense, right? Like, this is a little toy that someone has in their, in their palace or building. We're like, look how cool this is. We're heating it up and it's moving, right? And I mean, I think to us, we wouldn't be overly impressed. But I want to point this out because this was probably the first time that pressure from steam energy could be turned into work. And by work, I mean the ability to create like motion or mechanical energy. It gives us the ability to do something. In this case, the do something was impress your friends, but can you see how we've built on this concept year after year after year to create something more purposeful? Now, I want to remind you of another theory that we've learned about. There was a theory called the caloric theory. We discussed this earlier. Heat is not a concept that physicists have known about well for very long. Heat is something that we've only discovered in the last, 200-300 years. Because for a while they thought that heat was a massless substance found in all substances, and certain things had this phlogiston and certain things didn't. For example, wood has phlogiston. And phlogiston is this magical fluid inside, and as soon as it escapes through like fire. So certain things you can light on fire. Can you light this plastic on fire? Well, it'll probably melt, right? So this doesn't have phlogiston. But can you light this piece of paper on fire? All right, so this has more phlogiston than this stuff does. By the way, which other windows do I need to close here? I know some of you are squinting here. Do you want to maybe grab that window there, Nick? If that helps. Do you guys remember talking about phlogiston at some point, though? Right, so the idea that they just thought that there was this element that's inside of certain compounds, and sometimes it escapes, sometimes it doesn't. I need to put that plant a little bit tied down more. Okay, well, I want to share with you another innovation that was discovered long time ago. Gunpowder has been around for centuries, millennia. I believe the Chinese are credited with first discovering gunpowder. And this guy here, Christian Huygens, he recognized that he could make a piston. Okay. Do you guys know what a piston is? What's a piston? Sure, that'll work. A piston is basically something that goes, but usually we want it to go back and forth, back and forth, back and forth. Exactly. Yeah, there's a piston inside of your car. There's probably 6 or 8 or 10, depending on whether you have a V6, a V8 in your car. And a piston is basically it pushes and then comes back, and it pushes and then comes back. But that's the key, though, is that a piston doesn't just push and stop. It has to come back to its first location so that it can push again, right? Again, we're talking about mechanical energy, the idea of being able to do something with motion to it, right? Here was his first, and we can call this an engine of some kind. What he did is he had this long tube right here, probably some really rigid metal of some type, right? And inside in the bottom right here, he puts gunpowder. So here's gunpowder. Puts gunpowder down here. Now, this is in the downward formation. So it would have been that this object right here, this thing probably would have been down at the bottom at some point originally. He then lights a match right here, causes the gunpowder to explode, and what occurs? Well, this thing goes shooting upwards, right? Eventually it hits the top. But with how we set it up, is this little block going to stay up top here? No, eventually gravity will pull it back down. And when gravity pulls it back down, whatever the heck is on this rope right here, it's going to go up and down and up and down. I mean, in a way, you could have made an elevator out of this. I'm not sure it would have been the safest elevator, but I mean, that's more or less what this would have been. Now, I don't know what it is that you're trying to accomplish with this device, but you definitely can do something useful with this, right? If you are on the bottom of, say, a structure and you need to get something up to the top of the structure, blow up this piston, and you'll be able to make this thing go up and down. Right? So, well, yeah, you'd have to blow it up every single time, though, right? Which leads to, then, one of the most innovative designs I'd like you to know about. This is Thomas Savery's steam engine. Because you might think, okay, well, now we've got this concept of moving things up and down somehow. Well, the steam engine helped to accomplish something that we take for granted, obtaining water. We're so lucky. We live in a first world country. If we want water, I literally go to a water fountain, I put my water bottle underneath, and I get free cold water almost instantly. Right? Hopefully you guys can appreciate that there are places in the world where they don't have even anything close to that luxury. You may need to walk for 5 miles just to get your water for the day, right? So now put yourself back in 1698. People needed to get a hold of their water. They're probably pumping it from underground in a well, but they don't have pumps yet. They don't have indoor plumbing, right? So how do you get your water from your well? Well, maybe historically you might have had a bucket that literally you drop the bucket down the well, it dips in the water, you pull the bucket back up, and you got 1 bucket of water at a time, right? Savery has this idea about how to use a steam engine. And before I can explain how this concept works, I need to make sure that you understand how pressure and vacuums work. So I've got 2 short YouTube videos that I'm going to show you. And this is in lieu of me doing an experiment. Have you ever seen the pop can crushing stuff? I'm going to show you a quick video here, 2 quick videos.
This is 2 different levels of the experiment. The first, if you ever tried to crush a can, you get a soda can like this, and you go, hey, that can hurt your hand after a while. You do that enough. So why not just use this method, all right?
We need a device.
All right, so here's what happens. I have 3 soda cans that are empty, except for a little bit of water in the bottom. So I'm boiling some water in the bottom. See it kind of coming off here?
Yes.
Put your glasses on. So here's what we're going to do. Now that it's boiling, the water molecules have expanded and pushed all the air out. So here's the cool thing. Is if we take this now, I'm going to have you reach over, you're going to pick up the can, and then you're going to turn it upside down and seal it over the water. And I want you to watch what happens. Okay? All right. Insurance is paid up, is that right? So careful, that one, grab that one.
He is not here, no.
Turn it over.
Okay.
Oh, nice. Isn't that beautiful? It's not literally, it's the air pressure. All right, so we want to focus on the ball of water. We'll do it again. Okay? I'm sorry, the bowl of water. So focus on the bowl of water so you see the implosion. Yeah.
Here we go.
Okay, so just see the bowl of water. Turn it over. Oh, look at it happen. Isn't that amazing?
Oh, look, that one even went smaller.
That is small.
That one really went smaller.
here. All right. So let me turn it off here like this. So here's my glove, and so as we turn.
Okay. Well, we'll keep watching. I just want to make sure you understand this physics concept here. Okay. What's happened inside this can?
Watch what happens. Watch.
Okay. Caught it just right in time here. What's going on inside this can right here? Well, by boiling some water, what they've done is they've used steam to push out all of the rest of the air. So normally air is oxygen and nitrogen and carbon dioxide. What should be inside this can right here is only water vapor. Okay? But one of the cool properties of water vapor is that it boils at 100 degrees Celsius, right? So what if you take it from above 100 degrees Celsius and drop it down to a cold water temperature? What happens to the water as a gas? It turns back into a liquid. And in doing so, rather than being expanded, what do colder things do? They contract. What this creates then is a concept called a vacuum, which I think we've discussed before, where there's not a whole lot of molecules in the space right here. They used to be spread out, and all of a sudden they've contracted. And this uses atmospheric pressure. Really, two things are going to happen. One, a vacuum is going to form inside this can, and it pops. Why does it pop? Well, number one, there's too much pressure from the outside of the air on the outside. Believe it or not, the air around us pushes in on the can and causes it to collapse. You are being pushed by air molecules all the time right now. But the good news is the inside of your body is not like a vacuum like the can is. The can is basically completely empty, devoid of anything inside of it except for a few drops of water now. So therefore, when it gets pushed, it crumples, right? You and me and most other matter, there's stuff inside pushing back. So when air particles, I wish I could go back, but when air particles are hitting this can right here, there's resistance. But if there's a vacuum inside, it pops. Here's the other thing why that really matters, though. Watch the rest of this video here.
The cool thing is this here, watch this. As you lift it up, look, there's water inside. So in that implosion,
most of that water that came from inside was not just because it fell inside the water dish. Most of the reason why it came inside is that vacuum that was created, it caused water to get sucked up into the can itself. Okay? Think of a straw. What happens when you use a straw? Okay, so I'll just try to draw like a basic diagram here. I need to go find a new slide here. Where do I go? Okay, so here's a drink of water. Oh, let's not use yellow. You can't see yellow. Here's a glass, here's a drink of water, and here is a straw. So hopefully you'd agree that there's going to be water. I'll write H2O right here in the straw. But like in this part of the straw, there's going to be probably oxygen and nitrogen and carbon dioxide, right? Half the straw is water, half the straw is air. Right? Well, when you suck on a straw, what are you doing? You're removing the gases out of the straw, and you're basically creating a vacuum seal, right? Where what's happening is, as long as you manage to keep a seal around the outside of the straw by like keeping your lips tight to the straw, what ends up happening is if you suck all of the air out, well, now if the air is not there, you have what is basically a vacuum. Now, the vacuum will want to then draw the water molecules up into it to basically take its place. Otherwise, if that didn't happen, the straw would basically collapse on itself. Can you imagine a scenario where you take a straw, right? But then you plug the bottom of the straw so that nothing can come into it, and then you suck on it. Wouldn't the straw kind of collapse? Wouldn't that just be logical? Well, but what if there's something to be drawn up into the empty space? Well, then you have a siphon, you have a vacuum. And we actually understand a lot of these principles now better. This is the first time that this would have been used. This is Thomas Savery discovering how to use a vacuum concept to basically draw water up out of the ground. Let's see if this makes sense here. Boil some water right here. Make some steam. Okay? So the steam expands and it pushes up in all directions, right? As the steam expands in all directions, then eventually we cool it back down. And I don't know exactly how this diagram kind of works here. I don't love this one here. But can you kind of picture the idea of that if this steam right here, if you could cool it down in the exact same way that the can was, it would create a vacuum. And that vacuum would then allow us to be able to draw water up out of the ground, as long as there's some valves right here that we can control. Right? So you heat it up, you expand the steam. You use this water right down here to cool down the steam. You create a vacuum. All of a sudden that vacuum has to get filled by something. What does it get filled by? Water from the ground gets sucked up into here and up into here, and eventually maybe you can force it out of the mine entirely. Does that make sense? Cool. Okay, I think I have enough time I can show you the other video here. This is really less related, but this one's pretty cool. So this is the exact same project, only rather than with a tin can, it is with a big steel drum. This is 2 minutes long. It takes a little while, but you'll like this one. This is kind of fun. Okay. So while they do this, why don't I talk over top of it? I'll just turn the volume down because you don't really need to hear it quite that loud. So what's going to happen here is, hopefully you can see, they used a propane tank over there to heat the bottom of this can, right? So this can has steam inside of it, but they vented the steam, right? So what is the steam doing? It's pushing all of the air out, all of the oxygen, nitrogen, carbon dioxide, it's all out. That can should be full of steam. Why is the can not imploding? Well, the air around it's pushing in on the can, but there's steam inside the can. So the steam inside the can pushes the other way. Now, what they've done now is they've put this thing into a cold water bath. And they're hoping that what will happen is that the cold water will cause the inside of the barrel, the steam, to return back into water. And if it returns back into water, now you've created a vacuum inside this barrel where ideally there's no particles inside. That means that there's nothing to push back when the air around it hits it. So I'll put the volume back on. It took them a little while. They got a little impatient here.
Throw some water on it. Well, just grab the ice unit with your hands. That is so wimpy.
So why is that not going to help? Because we got to cool down the gas inside the barrel, right? Throwing ice on top is not going to cool down the gas inside the barrel. So here's what he's going to do. He's going to spray it with cold water, right? Isn't that awesome? That's cool, eh? Those principles that we just showed you right there are kind of the keys behind what made some of these initial engines work. So one more time, let's make sure we understand how the Savory engine worked. It pumped water out of mines, a very purposeful task, but it was inefficient and costly to do so because you have to keep opening and closing valves. Think of that last one we just showed you there. They heated the steam up. You could see the steam coming out, right? But they had to tighten it up. They had to close it all up so that eventually it caused the vacuum to occur. You'd have to close this valve here. You'd have to close this valve here and this valve here. And then all of this steam would then rise up, right? Use the water from the top right here, open this valve, cool down the drum. Now, you wouldn't want the drum to implode, though. So you wouldn't want to do it too much like what those guys did, but you'd want it to make it so there's a bit of a vacuum inside, so all of that water recondenses. But that vacuum, there's a void. Something has to come up and rush up and fill its space. So if you open up this valve and this valve right here, water, in theory, should rise up just like a straw, and you're sucking water up into both the cylinder and hopefully out of your pump. Really cool idea. All right, moving on. In around this time frame here, scientists were still struggling with what heat was, though. They were able to do things like the experiments I just showed you there, but they didn't know what they were doing. There's a guy that I want you to know his name. His name was Count Rumsford, and he had an idea. And I mean, I don't think to us it's a novel idea, but back in 1780, this was a revolutionary concept. Imagine that you're a cannon maker. So think Pirates of the Caribbean. You know, you're making a cannon on your ship to shoot at the ship across the ocean. And how do you make that cannon? Well, this is a good picture. You would have taken some sort of grinder, and you'd literally be grinding this metal out a big hole in the cannon. You'd be boring a hole in the cannon. Now, you guys probably already know what's going to happen. When you rub two materials next to each other, what happens to them when you rub materials? Yeah, friction is occurring and it's creating heat. But here's why this is perplexing back in the 1780s. At the time, they thought that was caloric. Remember this caloric theory that some things have and some things don't? Would metal have had caloric? Is metal an object that you can imagine that you would be able to light on fire and caloric would escape from it in the same way that a piece of paper or a log would? No. And yet, what's happening here is that metal, which is cold, doesn't have caloric, more metal, which is cold, doesn't have caloric, was heating up. And this perplexed Rumford because he was like, where is this magic heat coming from? Again, they really didn't understand what heat was back at this time. Here's what we now understand. Mechanical energy was being converted into heat. And that's one of the words we're going to use over and over in the unit, is the idea of energy can be converted from one format to another. Right here, I am taking magnet energy and I am converting it into electrical energy. Right here, they were taking mechanical energy, motion, and they were converting it into heat. Okay? But again, I just want to remind you, at the time, they didn't have any clue what was going on there. Okay? Here's another engine I'd like you to know about. This is Thomas Newcomen's idea. And I think that it works better if I just flip to the next slide, because I've got some animations, and then I'll come back to this one here. Take a look at this particular one. Oh, let's go to the animation one first. This is kind of cool. This is his engine, and he is using a piston. Remember what a piston was again? Something that goes up and down, back and forth, back and forth. He's actually got two pistons in this particular engine here. Let's start at the end here. The goal of this thing right here is to draw water up out of the ground. Right? We want to get water. We need water to survive. And so what's happening here is there's a vacuum concept happening right here, where as you pull up on the plunger, it's creating a vacuum, and the vacuum is sucking water up out of the ground. The nice thing about this section right here, you'll notice that this is only ever in blue. They didn't need to play the trick where they superheat the tank and then cool it down real quickly in order to create a vacuum. They just had this thing airtight sealed, and as it seals, it draws up, it creates a vacuum, it sucks the water up, right? So then the question is, well, what makes the plunger go up and down? Okay? Now, we could just physically move a plunger up and down, but that takes a lot of human power. We don't want to do that, right? So let's go over here to this side right here. This is how his piston worked. They heated up steam. The steam pushed this piston back down. See how the steam is pushing this piston down? But how do you get it back up again? As you push the piston down with red steam, we need to push it back up again. Well, by changing some valves, see how these valves right here are getting pulled in and out? We cause the steam to get pushed back up this way right here. Now, this animation happens really fast. The question then is, okay, steam pushes down here, steam pushes back up. Where's all that steam go? See how it just fell right down to here and turned into little blue water? Because that's the same concept we just discussed there, is they cooled it back down into water and then had it come out over here. Right? So steam pushes this side down, steam pushes this side up, open the valve, all the steam falls down here, we cool it back down, and then out comes the water. And this is a pretty brilliant idea, but it doesn't use the vacuum concept. It uses more the idea of using a piston and pushing it back and forth, back and forth. This uses the vacuum concept, though. If you make this thing here airtight, what should happen is as this thing gets pulled up, the vacuum draws the water up just like a straw. So I've got a picture here to kind of illustrate the concept. We've got our steam piston right here. We've got our main vacuum pump over here. And basically this back and forth seesaw helps to suck the water out of the ground. So I've got some written notes here if you guys would like to write them down. I'm going to move on, though, so you'll have to look on your notes here. But it used a piston, and it required that cold water valve because you have to get the steam out so that you can cool it back down. And because of that, these engines wore out quickly due to heating and cooling of parts. Remember that barrel I just showed you that imploded? That probably happened a few times in a scenario like this, where you're heating something up, you're cooling it down. You're heating it up, you're cooling it down. I bet you they went through a lot of destroyed pieces. However, it had been worth it because you get water. All right, moving on. I got to keep going here because I got 10 minutes tops. 1840, James Joule did an experiment I'd like you to know about. Joule was trying to discover basically how mechanical energy could create heat. And this is a simple little experiment here. All he did is he took a weight of different sizes, like say 100 grams, 200 grams, and he dropped it on a pulley system. And as this pulley system, as gravity pulled the weight down, it caused this little stirring rod to spin. Well, what have we now started to learn in the 1800s? Well, if you rub things together, it causes them to heat up. As this stir starts to spin, what's it going to do to the water? It's going to heat it up. He puts a thermometer in the water, which has now been discovered, thermometer principles. And he's trying to find a way to figure out if he changes the weight on this thing right here, he'll try to figure out how much temperature change there is. A bigger weight should, in theory, cause this spinner to spin faster, and the faster it spins, the more thermometer it should occur. So kind of a simple little experiment. Again, I point this out just to remind you that what we take for granted would have been revolutionary, 200 years ago. Wait, here's another one. This is James Watt. I'm actually going back in time. I know we just hit 1840. I'm going back to 1796. James Watt is also working on an engine, but I want to talk about the context of the time. This is beginning what is known as the Industrial Revolution. You probably learned about this a little bit in social studies class. If not, we're talking like trains. And what was really important about having trains is that you could now mass transport goods and people, mainly through Europe, like in England. And if you have the ability to have a steam engine on a train, you have the ability to now start to really accomplish some major innovation goals, right? Now we take it for granted. We've got trucks and we've got cars and we've got all sorts of things, right? But this would have been their main source of transport. This is James Watt's double-acting steam engine. I like this picture to help illustrate it. So this makes sense. What you do is you have high-pressure steam coming in. And based on this valve right here, do you see how either the steam goes through this side or the steam goes through this side? Never goes through the middle, though, by the way. The middle valve is always closed. So steam can either go left or go right. Well, if steam goes to the left, it pushes the valve one way. If steam goes to the right, it pushes the valve back and forth. And in doing so, you can make this piston go back and forth. And what's really valuable about this piston going back and forth is we've now managed to create motion in a piston. If we can now find a way to make this piston turn a wheel, now we can make a train run or an automobile go, right? And the brilliant thing about it is we don't need to keep heating up and cooling down different parts. All we have to do is make sure we vent out the exhaust, right? I mean, this is going pretty fast. I wish I could slow down the animation, but steam comes in this way, pushes it this way. Then the steam pushes it the other way, pushes the other way. And every time, though, we need to vent the exhaust back out. Because if you don't vent the exhaust out, then the piston won't be able to move. That's what I was trying to show you, by the way, in this animation right here, is that this piston right here, you have steam pushing it back up again, right? Pushing it down, not hard. Pushing it back up, also not hard, but we need to get that red steam. We need to drop it out of the bottom and get it out of the system, right? James Watt's steam engine is really brilliant. It uses the steam in both directions. So it's a double-acting steam engine. Okay. Here's what this led to then, the internal combustion engine. One of the most modern innovations. Also, though, we just talked about climate change. One of the things that perhaps by us making the internal combustion engine, we probably have contributed, not probably, we have contributed to changing the climate on our planet. Because here's basically the concept behind an engine in a car. First of all, there's no steam required anymore. Steam causes some problems. If you're constantly heating things up and cooling them down and heating them up and cooling them down, steam burns are very dangerous. So what we do is we do combustion instead. We burn fuel inside cylinders. Each of these cylinders is basically a piston that goes up and down. And I like this little visual animation here. As the piston goes up and down, it can make a wheel rotate in a circle if you're kind of clever about the engineering. This is what the engine in your car does. This is a V4. You've got 4 pistons running right now. And each piston is basically in a different stage. Here's a stage where something is blowing up. Can you guys see the power stage right here, how there's an explosion? That's going to force the piston down. But then the piston's going to rotate on the way back up, and it's going to push out all of the exhaust. All of the stuff that combustion turned into, so carbon dioxide and water, has to get pushed out of the system. Then, over here to the intake section, you better refill it with more gas, compress it, so that you can blow it up again. There's always 4 stages. There's the explosion stage, the exhausting stage, bringing in new gas, compressing it so you can blow it up. Send out the exhaust, bring in the gas, compress it, blow it up again. And this is what a modern engine does. Really cool stuff. Here's a picture that just kind of illustrates the fact that we always want to have at least 4 of these, but you probably have a V6 or a V8 or a V10, and all it means is that you have multiple pistons all running at the same time, and they're all at different stages. Here's one last animation to kind of show you what a typical engine would look like. Right? And it's really based on the pressure concept of all of these are always having an explosion one at a time, right? Just take a second just to look at it here. There's always an orange-yellow explosion happening somewhere. So now I'll just focus on one of these and just walk you through what happens again. So let's start right here. Explosion, release the gas. Fill up with gas, compress. Explosion, release the gas, fill up with gas, compress it. Kind of see how that just goes back and forth and back and forth and back and forth. And the whole time, this thing is turning some sort of crank, and that is giving us the motion we need. What's the main goal of today then? Although I was talking a lot about engine technology, we really want to discuss energy and the different forms. We're using chemical energy here. There's going to be light and heat. But most importantly, we really want mechanical energy, the energy of moving things. People, I think, are a little lazy. I don't think that's taking too far. Would you like to manually be moving things all the time? Or would you like to make a machine that can do it for you? I was recently at the airport. You know at the airport how they have those moving sidewalks? Right? So it's like you could actually walk from point A to point B, or you can just stand on a sidewalk and it'll move you for you. Right? I think that really epitomizes what human society has tried to do with technology, is find a way to make things move for us so that we don't have to. Yeah. That is very true, yeah. I mean, this is why humans innovate. Okay, I got one last thing that I gotta let you go here. Here's my last slide. To be honest, energy is still to this day something that we're trying to figure out what it is. This is a bullet point I want you to know right here. We actually have no one simple definition to answer the question, what is energy? Energy is still a concept that physicists are working on trying to better define. We know what some of the forms of energy are. Like we know about heat and thermal and, well, that's the same one, and infrared and chemical and mechanical. We know about the forms. But if you were to ask a physicist or a scientist, what is energy? It's not a really easy thing you can give an answer to. Here's the 2 things we know. Physicists know that energy is always needed to perform some sort of work or task. If you want to accomplish something with, say, like a machine, you need steam and thermal energy, or you need to have chemical energy. In order to do something, we need energy. And we also know that energy comes in different forms and it can be transformed. But to be honest, we don't really have a great definition of this. Physicists right now are even trying to explore the mysteries of dark energy. And I wish I could share more with you about that, but honestly, I don't know. And most of the scientists working on it don't know, which is why they're trying to study it. So that's where I'm going to end our lesson today. So last thought here, and then you guys can start to take off here. Here's the 5 things I want you guys to discuss in the reflection. I'm giving you 1 week for the reflection, okay? 1 week. Okay. Here's what we talked about today. Can you tell me about the different forms energy can take? What did you learn about pressure differences and how those allow you to do work? What do you know about a turbine and a piston? Remember, a turbine is something that spins around in a circle. A piston is something that goes back and forth. And then finally, here were some people who accomplished some ancient engines, Hero, Savery, Newcomen, and Watt. How did all of their discoveries eventually give us the blueprints for the ICE? What is ICE again? Internal combustion engine. Okay, so if I abbreviate ICE, I mean internal combustion engine. Okay, so anyways, the bell's probably going any minute here. Can you guys make sure you work on the reflection sometime in the next few days? All right, thanks everybody.